Physics Colloquium. Now, it is my pleasure to introduce you the first guest of the year, Dr. David Rakestraw. I'm going to read a short bio that he sent me. So, David Rakestraw has a BS in chemistry from Ohio Northern University, and then he jumped geographically and ironically to Stanford University, where he has a PhD in physical chemistry. He's now a senior scientist at Lawrence Livermore National Laboratory in Livermore. More than a decade, he led multidisciplinary research and development to counter chemical, biological, biological, nuclear, and explosive threats. Over the past 5 years, he has focused on STEM education, where he's developing inquiry-based activity that take advantage of the sensors in cell phones. And I believe he's worked with our department in that regard. Prior to Lawrence Livermore, he spent 12 years at Sandia National Labs, also in Livermore, where he engaged in a wide range of research and development activities, which began with the development of laser-based diagnostics for studying combustion processes. For 6 years between his time at the two national labs, he also co-founded a company that specialized in applying microfluidics for chemical analysis. I read his longer version of CVs and impressed with all the methods that modern chemists use, including NMR and laser spectroscopies and so on. Without further ado, welcome to our guest, David Rakestraw.
So, glad to be here. It's an exciting time to be a scientist, an engineer, somebody going into medicine, and the capabilities that are available to people today are just remarkable. So I'm jealous I'm not younger, and that I was in a place to take advantage of these tools. But I think we see a lot of advances in science and technology and the tools that we have available for us to do science and engineering over time. I entered graduate school at a time where lasers were really at their early stages, and it really opened up opportunities to do all sorts of new scientific activities. You're at a time where you're seeing these tools of how computational tools have now enabled this artificial intelligence, which I think is truly game-changing on society. And what I want to do today is show you some examples of how one can use this to help advance our scientific learning in particular, right? There's lots of things you can do with it. We're going to focus on how it can be used in educational domains. Okay. As you heard, a lot of what I've done over the past 5 years is take advantages of the microelectronics revolution that has enabled us to have all sorts of sensors integrated into the tools that we carry around with us every day. These tools are incredibly powerful. The richest companies in the world are spending hundreds of billions of dollars a year advancing the technology in these devices, and they are especially valuable for us to use in doing measurements and for doing science and teaching science. And so I've been focused on that. I've created thousands of pages of material that is all free to download on the Livermore website that talks about these kinds of experiments. And so you can find some of them there. There's almost no AI stuff on there yet, because everything that I've done on that has been in the last year, less than a year, 9 months. Okay? So we start off with having something we want to measure, right? So whether it be you know, sound waves, electromagnetic waves, pressure, magnetic fields, all sorts of things that we might want to measure, okay? We then have all of these sensors, and these sensors are all available inside your phones, right? Where we have, you know, antennas that are detecting microwaves that are coming down from satellites circling the Earth. We made a measurement this afternoon using that capability. We have pressure transducers that can measure the pressure change from this tabletop down to the floor with high precision. We have the ability to measure any kind of motion, whether it be rotation or acceleration. And so those sensors are all available to us to make measurements. They make measurements kind of in the analog space, but so much of what we do with measurements is now in the digital space. So we do computational analysis, and in order to do that, we transform that to the digital domain. And then we have all of these processing things that we can do with that massive amount of information that we can collect with all these sensors, right? And what I found is that this is a place where there often is a barrier in some of the things that I wanted to do with students because we get caught up on the syntax that's being used and the software tools that are used to do the analysis. And so I'll spend all my time walking around trying to find out, you know, where the missing parenthesis is or semicolon is in somebody's, you know, code or in their spreadsheet because they're not getting the right answer, right? And instead of talking about and understanding the science and the concepts, we end up basically worrying about, you know, syntax and how to do stuff. And then there's all sorts of things that are just not possible to do because the mathematical difficulty of it, of implementing it is just too difficult for, you know, many students at the, you know, particularly at the introductory level, okay? So, but that's changed now. And with the presence of AI, these things are now possible. So what I started using it right away, and I thought it was just an incredible tool, but it still had a lot of limitations in it. And what you can see is we went from 3.5 to 4, GPT-4 to GPT-5. The capabilities have dramatically changed. So, so I don't know how many of you guys are using AI to do stuff. Is anybody kind of trying to stay away from it, ignore it? Maybe some of you? Yeah. So I know a lot of people who used it, you know, a year ago, okay? And a lot of the stuff I'm going to tell you about today is if you tried to do this a year ago, it wouldn't have worked, okay? Because the models weren't good enough yet. And the improvement has been just incredible. And so when I read, I'm very engaged in this. I read about it all the time. But I won't read a paper on that's a year old now because the deficiencies and the things that they're talking about are irrelevant because the tools have changed so dramatically that that's just not useful information to talk about. So any anecdote or caveat or concern that somebody had, you know, about something not being able to do something a year ago is just not significant. What I'll also tell you is that a lot of what I'm going to show you today, the OpenAI ChatGPT is much better at than Gemini or Claude, which are the two other large language models that are fairly popular. And much of what I'll show you today, those models still don't do well. Okay? there's a proliferation of tools being generated for education. You know, you guys are being bombarded with, you know, all sorts of ways of using AI to help you do your jobs and to help students learn. We're only going to focus today on using AI as a co-investigator in doing kind of helping us learn and discover through data analysis of data sets. So that we're going to focus on how can we use this in lab activities where we're using it to help us understand, interpret, and evaluate real data sets. Okay. So so you heard my bio. What that meant was I started doing this stuff a long time ago. And so when I first started, data analysis looked like I was doing chemical reactions in the gas phase, and then I would take some complex mixture of gases, I'd separate them using gas chromatography, and when the molecules came out the end of the column, right, we had basically a thermal conductivity detector that would basically measure the conductivity of the gas, and it would give you basically a signal is that conductivity changed when those molecules came off the end of the column, and we would record that change in conductivity with a strip chart, okay? And the signal, kind of that change in signal is a function of time. So the strip chart's going along, and when the molecule comes out, it draws this little peak, and that peak was proportional to the amount of material that was there. I used this like hand little calibrant instrument that you'd run that thing over top of the peak, okay, kind of in a circle, and it would tell you basically what the integral of that peak was. And then I would track those numbers, how much material was there based on some calibration that I did, and then I would hand draw a graph that would show kind of what the concentration of different molecules were as I changed various conditions, right? Exceptionally time consuming, very difficult, but you know, my professor would tell me, you know, it was good, honest work, right? You know, learning how to be a scientist. Well, I can tell you that, you know, that's, you know, not all that interesting. So what we're going to do today is we're going to take a rapid tour of how that has changed. So how making measurements and how doing the analysis, how visualizing the information is all dramatically changed from what it was many years ago, right? And I'm doing this contrast to a long time ago, but the fact is that there's a big change from just 3 years ago to what it is today. And it's a challenge to try to understand and figure out how to do that, right? Because usually these transitions in technology don't happen this fast, right? This has happened dramatically quickly. So the lab has been using AI for a long time to do stuff, but there was really a small group of people who were really, you know, experts in machine learning who had access. And these large language models has changed it so every one of us as a scientist can communicate using natural language to get, you know, large complex codes to run and do analysis for us. So, so I'm going to take you through a variety of examples that are intended to show how we can use some of the capabilities of AI to do things that maybe we weren't able to do as easily otherwise. Okay? So uncertainty is a topic that we all teach in, you know, in science classes. You know, any of you who are educators, as students, you know, this is like the most boring part of any class, where you have to sit down and learn about this friggin' uncertainty things and the statistics and all of that. And, you know, and it's super painful, right? And there's always a risk when it's taught at the beginning of a class, right, that you just lose the people and you're done, right? Because this is such a boring class, right? So, but are there better ways to do this and to help things sink in? So I'm gonna see if I can help some things sink in for you guys today that maybe you didn't fully appreciate, even, you know, your senior scientists here. So what I'm going to do is I'm going to measure 0 30,000 times with the phone. Okay, so that means with an iPhone that's collecting data at 100 points per second, I'm going to basically sit it on the table, hit go, and I'm going to collect gyroscope data for 6 minutes, and I'm going to get 30,000 data points. Okay, and now I'm going to look at those data points. And so the first thing I want to do is I want to understand if this is random noise, right? What does that random noise look like? Both when I'm making a small number of measurements to when I'm making a large number of measurements, right? And oftentimes the way we do that is we create histograms that will tell you how many measurements, you know, fell within a certain range, right? So there's going to be some expected value, which is 0, right? And we're going to hope that most of the measurements fall pretty close to 0, but we'll create like a little bin that says everything within a certain plus or minus of this value. We'll count how many events go in that. Then we'll count how many that fit in the bin next to that, and the bin over here, and the bin over here, and we'll plot those up, and that will tell us kind of like how our measurements are scattered around its central value, right? Has anybody actually created a graph like that recently? Not just like choosing histogram from the graphing thing, but to actually know how to take a large data set, bin it up create all the individual bins, and then graph those up. Okay, so some of you might have done that, but it's not that easy, right? You got to have the data analysis package, or you got to have a software program that does that. It actually takes a fair amount of effort. What I found is teaching introductory physics students how to do that task, you know, might take 30 minutes. And the question is, do you want to spend 30 minutes doing that? So I would say no, and so instead I can ask ChatGPT to look at this data, and I want to see how the distribution is changing as I go from a small number of measurements to a large number of measurements, right? So I'm going to say 25, 50, 200, 1,000, 30,000. Show me those plots for multiple different times in the experiment. I won't bore you with all of them, so what do you guys expect to see? So talk to your neighbor. What do you guys expect to see in this analysis? You guys aren't talking to your neighbors. You guys got to sit next to somebody, what do you guys expect you're going to see for small numbers and then large numbers? What do you guys expect to see? So for the small ones, what do you think for when you have a small number of samples, what's it going to look like? Kind of scattered and random, maybe? Kind of like
maybe with, you know, unusual peaks and stuff like that.
Yeah, so kind of
a mess.
Yeah, it's kind of a bit of a mess. And then once you get to a large number, what's it look like? A nice smooth bell-shaped curve, right? So this is what you get, right? And so this was like what ChatGPT gave me as the output from that question, right? And now I get a bunch of things with both, and it decided I might want points, but it also did the histograms, and you can see how at the beginning, and I had these for multiple different times during the data set, because you're only looking at this really tiny, you know, spot, and you can see how it kind of, the distribution early on, you have no idea what the real distribution of numbers looks like. okay, in these small numbers, and the average is going to vary. But as you go to more and more sample sizes, you get something that's really nice. And you thought of, anybody, what's the name of that function? Gaussian, right? So I could say, it actually asked me if I wanted to compare it to a Gaussian, so I said yes, I'd like to compare it to a Gaussian. For the graph, use the data points to represent the value for each bin. Plot the Gaussian as a smooth function across the X range. And it does that for me, right? And so you can see that it's this beautiful, nice Gaussian function. And this is all data your kids collected themselves, right, that they're doing analysis on. They're not doing it on some data set they were given or provided. This is data that they collected with a phone that's in their pockets, every single day. Okay? And if you had to do this in a spreadsheet, right, this is like a full lab period, right, to do this kind of experiment, right? And you can do this in 10 minutes, in your class. Okay? And this is one where most of you guys have done this in your statistics class at one point in time, right? But I really wanted to show what these standard deviations, because we always use these standard deviations. Most of the time nobody actually calculates standard deviations by hand anymore, right? You're putting them in, you're using some software to basically go through and calculate the standard deviation. And it gives you some number, right? And you got like 1, 2, 3 standard deviations. And so I wanted to see whether I could take this data and help students kind of lock in, what a standard deviation looks like. What's that mean in terms of probability? So talk to your neighbor. What percentage of measurement should fall within one standard deviation in a Gaussian?
65?
Yeah, I think that's the standard value.
Yeah, so a lot of you guys, what about 2 standard deviations?
No,
Yeah,
3
and-
standard was 95.
And 3?
99, sorry.
Okay. So a lot of you guys know this, but for many scientists, these are hard numbers to keep in your head. You did it one time when you did this integral. But here's basically, I think I skipped a slide. So here was the histogram, and you can actually see how many measurements were made in each of those bins that were 1, 2, and 3 standard deviations, right? Because I told it to make this and calculate how many things were in there, right? That would be a pain in the butt to do if I had to set it up in Excel or something else, right? But I do this with a couple sentences in ChatGPT. And you can see it comes out to 68%. I had to do it for all the different, in this case there was X, Y, and Z axes, so I did it for all 3 of them, and you get statistical numbers. But you can see that the actual measured values matched up really nicely with the theoretical values of the integral that you would get when you integrated over a Gaussian distribution. So we can assume that this sensor, the gyroscope on your phone is basically the noise on it is being generated by random sources that is creating a Gaussian format. Okay, so that was a bunch of statistics that really kind of lock in things that can be done pretty quickly, and you can look at and visualize things that are typically not done in a regular class, right? It's almost all theoretical, and we made it real experimental. Okay, so this is an experiment that several of us did this afternoon. Okay, so what we did is we used the GPS in our phone, so we got a little microwave detector in here, right? Microwave chip that's detecting from 3 or 4 satellites, in many cases more, but at least 4 satellites that it's detecting to get our position. And basically measuring latitude and longitude over time. And what we did is we started at one spot, we started in front of McLean, we walked down to where did we walk to?
Thomas Administration.
Thomas Administration Building, that way,
yeah.
and then back, right? And so we got something that looked like this, except it was reversed because we walked a different way. So, so basically I took that GPS data, I put it in, and we get data that looks like this into ChatGPT. I think, so this is, everybody remember what latitude and longitude is? So longitude lines go up and down, latitude lines go around the Earth, okay? So what can you tell me about this particular walk? So those are, by looking at this data, what can you tell me about the walk that was just taken?
Walk north and then back south.
Walk north and then back south.
Mm-hmm.
And how do you know that?
So isn't the latitude increasing?
Yeah?
Longitude seems to be approximately constant.
Yeah, and the longitude is approximately constant, so you're walking along the longitude line.
Perfect. You can see dodge stuff.
Yeah.
It's better.
So, so you can see that, and so what you can do now is, if we wanted to know how far we walked, the way I was having students do this before is they would take the Haversine formula, they would basically use a small angle approximation, they would come out with these equations that would allow them to convert from latitude and longitude to basically Euclidean coordinates, okay? And this shows you the individual calculation. You got to use like 8 or 9 significant figures in the latitude and longitude to do the measurement, and it's, you know, quite a challenge to just do the logistics on this. What I typically did was, but if I take this and I put this data into ChatGPT, I can ask it to simply calculate the total distance and displacement, use the small angle simplification for the Haversine formula, and it will actually do the analysis for me and create the graph of displacement and distance as a function of time. Okay. I then wanted to know what the velocity was, so I asked it to find the transition points, and then I asked it to basically move a little bit away from each of the transition points and fit the slopes of the lines, and you get these two graphs of the distance versus time, right? So now you can use, instead, in an introductory physics class where you're teaching people about, you know, position versus time graphs, which again is one of these super boring topics, here's a way of essentially using satellites, microwaves, their sensors in their phone to do all of this stuff to come out and learn about position, and you're pulling in all of this other remarkable, interesting physics into the discussion while you're doing it. And you can do the mathematics of it. You know, you can include as much as you want of having them get help with the mathematics by just explaining it, you know, conceptually to ChatGPT. If I wanted to do it in a spreadsheet, this, for example, shows one of the calculations of distance, and I've done this before with students, and I spend all my time basically making sure that they get the equations typed in right to a spreadsheet, because none of them get the right answer initially, and there's always something wrong with that. So then I ended up giving them just a pre-made template spreadsheet, which seemed stupid, and so now I feel like, well, I might as well just have them explain what they need to get done to ChatGPT and let it do it for them, rather than giving them the spreadsheet and just having them type the numbers into it anyway. So this way they can at least have to explain what they're trying to do to the chatbot. Okay. So their equivalent of this. You want to give this part of your talk? So you can do a similar thing on an elevator with acceleration in terms of measuring distance. And so what we're going to do here is we're going to look at, this is acceleration versus time that's measured on an elevator. So this is one sample data. So I now took this data that I collected on my phone, I put it in ChatGPT, I had it calculate the y-axis. So when I was up in the elevator, I stuck the phone against the wall like this, and that's the y-axis of the phone. And so we would see acceleration going up and down along the y-axis. Talk to your neighbor and tell me what can you say about this data? What's going on at the different locations in this data set?
From a high level to a low level,
So I'm holding my phone. My phone was against the elevator wall like this. This is the positive y-axis that way.
No, it's
So I went up and I came down. Okay, what's I don't think what's happening right here? Going up in constant velocity. And then I stop, the door's open, it's very stable for a minute, and then I come back down. So I basically accelerate going down, and then I come to a stop, and then stopped at the end.
I like the rumbling, you can see the rumbling of the elevator.
Yeah, so you can see all that, and the question is, how much of that's real? How good is this data? And what you can do is you can basically take this, and you can now say, I want you to analyze this data. I want to use the first, this data you can see is basically, I did it on purpose. I measured acceleration with gravity. So it was measuring gravity, and then it was measuring the change in acceleration in addition. So it was all centered around, 9.8 or something. And so what I said is I want to correct for that offset. So it basically used the first 6 seconds of data, subtracted that from the whole data set. So now I have a data set centered around 0. Okay, and then I basically wanted to do calculate the velocity. So the way I've been doing this in class, and the way many people have been doing it in class, is they basically use numerical integration. So you take the measurement of your acceleration, you multiply that times the period of time between each individual measurement, and you get the change in velocity for that increment. And then you add up each of those increments over time, and you can calculate what your change in velocity was. And if you assume your velocity was 0 at the start, you then know what your velocity was at every point in time, during the experiment, right? And this can all be done in a spreadsheet and add these up over time. This just shows you, doing it in a spreadsheet. So the first thing I had to do is calculate an offset, recalculate a corrected acceleration, and then I'm going to do this integral of the acceleration. Alternatively, I can basically say put this data into ChatGPT, and I can say integrate the corrected y acceleration, determine the velocity at each point in time, plot the acceleration and velocity on the same graph, and basically you get this, right? And we got a validation experiment right here. You just did that after our little workshop, and your data looked just like this, right?
Yep.
And then, of course, you can do the same thing for integrating the velocity to determine the displacement, and you can basically get the displacement as a function of time. Okay? So these are all things that you could in principle do in a spreadsheet, but depending on, you know, how your class is going, different times, because this numerical integration is something that can be used in a lot of different ways to look at sensor data. And my sense is that you can do it once where the students do it by kind of in a spreadsheet where they're adding up individual increments and they're kind of seeing how to do it. But then as you do more and more experiments that require you to do that in the future, you know, this seems like a very good alternative, right? We saw in our workshop this afternoon that you can do the same thing with gyroscope data to go from angular velocity data to angular displacement data. Okay? You can use the pressure transducer on your phone at the same time to measure, you know, going up and down. This was a measurement that I did at the AAPT meeting in DC in the hotel. And so this was basically measuring the pressure as a function of time as I went up. And then, oh, I think I maybe asked you. So I won't tell you, I started to say something, but I might have been wrong. So what would you say about this escalator ride? What direction am I going? And what's going on here?
Going down. Going down.
And
then back up.
then back up. So down, wait for a while, then go back up. So that is true. And so, but I can now take the hydrostatic constant of 11.5 pascals per meter, which students can actually measure and get from experiments in the classroom. And now they have a way of measuring changes in height as they go up the football stadium or go up the elevators or walk up the stairs in the back of this auditorium. And now you can, you know, calculate, you know, what the change in height is. It basically drew a line in for me and told me what the displacement was for that escalator ride. And then what I did is I told it to calculate the slope of the graph between 20 and 50 seconds. I meant to say slope, but it figured it out for me. And so then it plots the regions, plots the change in pressure, does a fit to it, tells me what my velocity is, and not surprisingly, the escalator is going the same speed up and down that it went up. So those are, again, you know, simple ways you can do it. This was an experiment we also did today, earlier, where we wanted to measure the velocity, the angular velocity of a fidget spinner as it spun from going very fast down to very slow as a simulation of a tachometer. Okay, and so what we did is we put a magnet on the fidget spinner, we spun it next to the magnetometer on the phone, and basically looked at the modulation of the signal as a function of time. Okay, I had it plot this data so that you could look at early, middle, and late times. Very quick, easy way to visualize the data, because it's really hard to tell from this what the data really looks like at the early stages, right? And so if you want to kind of look and decide how might I want to analyze this data. What do you think what would be a way to determine the period for each rotation here? What would you do? Yeah, so you go in and try to find each maxima or minima.
Mm-hmm.
Yeah.
You only put one magnet on this.
Yes,
Not
yeah, there was just one magnet on it, yep, so you got one kind of cycle per rotation. Okay, and so, and in this particular case, would you think the minimums or maxima would be better to use?
Maximums. No, the minimum are very shallow.
Mm-hmm.
Yeah, so the minima are sharp, so those might give you more accurate periods of time, right?
Mm-hmm.
And so we could, so students can look at this, decide, and all the data will look different than this because everybody's experiment is set up a little bit differently. They point the magnets in different directions, there are different orientations relative to their sensors, and so everybody's data will look different. They'll have to make decisions. Basically, you can go in and you can tell ChatGPT to find all of the minimum values, show you that it's doing it correctly, and then you can plot the angular velocities as a function of time. When we did this in our class, and when I've done this with students, the ChatGPT generally doesn't find all the minimum or maximum quite right the first time. And so you get a real messed up plot. They have to figure out why that's the case, know what questions to ask, and then they have to add constraints in to help them find the minima. Just like you would if you were writing code to go in and find a whole bunch of minima or maxima in a data set. And so students do the same thing, except they do it using natural language instead of having to do a bunch of if, then, or equality statements in code, right? And essentially you say it in natural language and it gets incorporated into code for you. Okay? This is an experiment where I did this one when I taught a physics lab in Cal Poly last fall. And what the students did was where they basically placed their phone on their hands. And so your hand was basically hanging off of an edge like this, and the phone sat on top of your hand like this, okay? And what happens is your brain is trying to hold your hand in its equilibrium position, okay? And there's a control loop, and it's called your physiological tremor. So your hand's actually going back and forth as it basically goes back and forth between the equilibrium position. And that's kind of the control loop speed of your brain to your muscles and tendons. And so what you see, particularly on the z-axis there, is not a bunch of random noise, but you see a modulation frequency that is associated with that oscillation. You could go in and look at the data, and this is how I started to do it with students, and you basically just find regions where there's multiple kind of modulations that look symmetric. You can find the times and calculate the period from that, and then calculate the tremor frequency. But you can also go into this. How else could you determine the frequencies? With the Fourier transform, right? And so what, if you wanted to do a Fourier transform in Excel, you got to do a lot of different stuff. You got to use, imaginary numbers, and it's possible. And I showed students how to do this in my slides, but they don't like it very much. And but it's a multi-step process, and you can use Excel to generate Fourier transforms. But you could also basically take your data, put it into ChatGPT, and then basically tell it that you want it to do a Fourier transform on the data to basically plot a power spectrum. I put some extra stuff in here because sometimes when you do a Fourier transform, you get a large value at 0, and so I just had them knock that data out. And then you can get a beautiful power spectrum like this for what the frequency of the tremor was, okay? And while this is pretty straightforward for a single frequency tremor, there are oftentimes more than one frequency involved, particularly, so there's this physiological tremor that you have, but there's also neurological tremors that students can have and anybody can have. And so this is an example of one of the students in the class that knew she had additional neurological tremors, and you could see that there were actually two tremor frequencies that you got once you actually did the Fourier transform, which we would never been able to do from the kind of handheld, visualization data. And because we could do this very quickly, I had students being able to do other things. So I brought in like a cooler full of Celsius energy drinks, and they all like pounded, well, a bunch of them decided to pound a Celsius energy drink and then measure again. Some of them ran up and down the stairs. Some of them put an extra weight in their hand. And they then could do a variety of different experiments to try to understand how different things affected tremors. And we talked about how this was at the cutting edge of research right now, where people are using accelerometers to measure the impact of drugs on things like Parkinson's disease. And that they got to do these experiments in their classroom and could analyze them using these sophisticated methods. And so I actually had 5 students in my class write a paper on this. This was like the fastest paper I ever had published. I sent it in January, and it got published in the April 1st issue of the Physics Teacher. So it was like a month and a half from when I submitted it to when it appeared in the journal. And it was pretty cool, because I had 48 kids all go through this and do this. Very effective. They all loved this experiment. And and it would have been really difficult if I would have had to to make them do the Fourier transforms in Excel. They probably would have all just hated me, at the end. But because they could use AI to do this and get the data out, it was all very exciting to them. You can also use this to analyze any kind of periodic data. So this is data from not the hippo, but me singing a note. So I popped this into ChatGPT, it graphed it up for me, and then, so what do you think the frequency spectrum is going to look like for this? So if I do the Fourier transform of this, what's the frequency spectrum going to look like?
Yeah, there's 2 peaks in there, the same the double iPhone. So I didn't sing on pitch.
Yeah.
400.
Yes. So, and what's the pattern? What's the pattern going to be?
3 double peak, close together.
So anybody remember like what a string oscillator looks like? So you got F, 2F, 3F, 4F, 5F. So basically your harmonics are, you got your fundamental, and then all your harmonics are multiples of the fundamental. And so, this is what you actually get is the power spectrum. And so students love being able to do this because they can do it so fast, right? They just sing into their phone, they capture, half a second verse of data, they send it into ChatGPT, they tell it to do the Fourier transform, and then I had them, move the try to sing higher, and they would, see the fundamental move up, and they could do all these really interesting experiments with this. Let's see. This is an experiment that we also did this afternoon, where we looked at the transmission of light through a finger. Okay, and so we have the lights in the room going through your finger. Your phone sits on your desk. Your finger goes over your front camera. You basically take a video of the light from the ceiling transmitting through your finger, being absorbed by the blood in your finger. as your blood pumps in and out of your finger, it will change the amount of absorption that takes place, and we can measure that. So this is kind of taking the video. This is what you'll look like on your screen. In many cases, you can actually see the visual fluctuations. I think you guys you guys see it fluctuating visually?
Yeah.
When you done it, yeah. So you can actually see, in many cases, you can see it visually yourself, but even when you can't see it visually yourself, if you average over, 25 million pixels for every, 1/60th of a second, you can actually get very, very high quality absorption spectroscopy data, or transmission data. And I used to do this in a video analysis software, but instead you can take this file, you can upload it into the AI, you can tell it to basically average the overall intensity of all the pixels in the frame, give you an average value, and then plot it up, and then you get a plot that looks something like this, as the blood pumps in and out of your finger. I have it inverted here, where essentially what you see on the rise is when the blood pumps into your finger, okay? And then the fall is where the blood is flowing out of your finger, okay? And that little modulation that you see there at the top, it's called the dichrotic notch. What that is basically when my heart pumps and it pushes blood through my arteries. Basically, it stretches them out a little bit, and then there's this like reaction of it coming back. It gives me that other little push there, at the, kind of increase in pressure at the top as it basically tries to contract back to its original size. And when you're old like me, your arteries are harder, and that moves closer to the initial peak. And what we saw in our classroom today was that for younger people, that notch gets pushed out, further in time, and you can see the notch, right? You got to see it, got to see it move out.
My table was crap.
I'm like, oh, okay.
So this allows you to do, really interesting spectroscopy in the class, and to do it relatively quickly. So again, it shows you a different type of mode of data, so being able to analyze, complex video with this induced spectroscopy. There's a lot of things you can do with other types of data. One of them is collecting this measurement we just did. Your watch can collect this data as well. It actually stores the beat-to-beat data, because it turns out that your heart rate variability is a really important health parameter. So what you might think that having really steady beats is the best thing, but it's actually not. It turns out you want to have a reasonable amount of variability to it, because your body wants to be able to change and change the amount of blood that's being pumped in based on physiological properties, or if, Doug starts chasing me, I want to be able to run out of the room, quickly and get my heart rate up. And so there's a certain variability that you want in there. So it turns out this is one of the, a parameter that's very tightly coupled to longevity. So people who have higher heart rate variabilities tend to have longer lifetimes. And so the Apple Watch measures this, but when it gives you, if you go in here and you get the data, it basically just gives you a long list of numbers on when each beat took place, okay? And, but what I did in this case is I then just took screenshots of that data. So now I have each of the times associated with, so if you can't see it from the back, it's like 6, 54, 47.44, right? So it's down to the 10 millisecond time frame. And so you can now basically, I took those screenshots, put them into ChatGPT, so these are now 3 pictures with a bunch of columns of numbers in them, okay? I told them that this is what I was giving it, and I wanted it to basically create a file where you basically order those numbers and plot the intervals as a function of time, and this is what it produced. It turns out that there was actually a gap in there, and that it showed me, and then I told it to take the gap out, and it automatically corrected for the gap and fixed the time scale, and so now I can measure my variability. Okay, I have one last thing that I wanted to show you. This is EKG data. So you can collect EKGs on your on almost all the smartphones. You can go in and have it find all the peaks associated with your EKG, and you can also then determine your heart rate variability from this data, which is actually better than the other data because this is at 512 hertz that it's collecting the heart rate variability data. And this, basically what I did is I gave it this file, which is a long file of all these heartbeats, right? And I said, you know, are you able to overlay the cardiac cycles by lining up the 29 R peaks? So the R peak is that one peak right there in the middle. I'll tell you, my daughter was doing research at Duke, and she's a computer science, biosciences double major. And she was doing research, and she had this problem to do for her research, where she was getting these large data sets and wanted to look at the variability over these cycles. And she took about 2 weeks to basically write the software, to read in the data files, to basically smooth data, analyze, identify all the peaks, cut out sections of that data, and then overlay them all and create graphics that you could do from it. And so she, you know, was very proud when she sent me this data about a year ago when she did it. And then I told her I could do it in one line in ChatGPT and produce the same kind of graph. So pretty remarkable stuff that this is capable of doing. You know, and until you ask the questions, I mean, a lot of times I wouldn't even thought to have asked this question, you know, of this data set, right? But what I found is that almost every question that I ask to work on any of these data sets I collect, ChatGPT has been able to do it effectively. So from character acquisition in pictures to videos to large numerical data sets to doing transformations from coordinate systems to numeric integration. All of these things are now Fourier transforms. All of these things are now possible and can all be done by somebody with no modern programming expertise, and just using natural language to do all the analysis. So with that, I will take any questions that you have.
Some questions? I'm just thinking in terms of students and their grasp of technology as it goes along when capturing and processing this information with AI. Are there any concerns that processing by AI is going to lose a lot of the skills that are necessary to analyze these things from scratch rather than relying on something else to analyze it for them?
Yeah, I think that there's a lot of, that's a huge concern. And I think that what I've done over the last 9 months is primarily look at what's possible to do, and I really think it's now up to us as a community to start to think about, okay, how do we now take this incredible capability, and how do we integrate this in to the learning process? And so I tried to show you at least some examples today of, here's some things we can do that you would have never done otherwise, right? So we can visualize the statistical data, you know, in ways that we would have never done in courses before because we didn't have these tools, right? We can do these rapid Fourier transforms that we just weren't going to do in an introductory physics class with a bunch of pre-meds, you know, in the past. But there's other things where you'd say, well, isn't it important for them to maybe learn this method first? Or, you know, how would they even ask the right questions if they don't have, you know, some background, or we haven't brought them through a process, you know, first, right? And I think that is, you know, where there's work to be done for all of us, is figuring out how to most effectively do that. But I think that what I know is that these tools are going to be incredibly important for any scientist, engineer, doctor to use in the future. And, you know, so we need students to know and learn how to use them, but we have to make sure that they understand the foundations as they're applying them. And so figuring out what's the pedagogy necessary to do that, I think, is, you know, the challenge we're going to have for the next few years of exploring that, trying to understand how to best use these. Because I'm not telling anybody here today that this is the, you know, we should use this, you know, blindly, you know, to just do things faster or make things easier for students, or skip things because there are parts that we don't want to skip, right? And so I think those are all things we still have to, you know, figure out. But I'm excited because I think that very few people, I mean, I presented this at the American Association of Physics Teachers meeting in the beginning of August, right? And, you know, there was a room of, you know, 80 people or something, and I don't think there was a single person in the room, you know, who all were people who were interested in AI that had any clue that you could do a bunch of this stuff with AI, because people were still stuck in, you know, asking it a question and going back and tutoring. I mean, this approach is just really, you know, people don't know, right? So you're some of the first people who are getting to see what's possible with this. And like I said, a year ago, you couldn't do this. You would have asked it to do some of these things, and it would have just crashed, and you would have said, doesn't know how to, can't do these things, right? And if you ask Gemini, if you were a Gemini user or a Claude user, and you ask that tonight when you go home, you'd think it still can't do it, because, you know, many of these things it can't do. Yeah.
So I have a friend, and she's an attorney, and she was using ChatGPT, but I think it's been more than a year, and she had to stop. She had to stop because it was hallucinating citations and so on that could get her disbarred if she were at. So I mean, she's pretty diligent about checking everything that it does. Is there a difference between the way ChatGPT works for somebody who asks like some kind of lawyerly type question and then like ChatGPT doing data analysis like this when it comes to possible mistakes or hallucinations?
Yeah, so what I would tell you is that, you know, a year and a half ago, there was a lot of what people call hallucination going on. Models now are, you know, using a lot of real-time computation and doing what's called, you know, things that we call reasoning. So a lot of the stuff I've done, you know, they're like 15-step processes that you have to go through, right? I mean, there's stuff that I would never ask a student to logically figure out how to go through. And ChatGPT now with these reasoning models can go through them. I don't see, I do probably every other day, I do a deep research report on some, complicated topic. And, in the last few months, I've never seen a reference that wasn't real. Because I go and check all the references and, or the references that I'm interested in. And I've never tried to go to a reference that doesn't exist. So those problems, which were early problems where they were citing things and, they don't exist. So like when I asked to do a bio on me 2 years ago, it talked about my, involvement with the National Admission Facility, which, was natural for it to think that I was involved with the National Admission Facility because it was a big thing at Livermore, but I've never been involved with it, right? But today it wouldn't do that. Today it would basically nail only things that are really on the record that I've done.
I was going to ask a question along those lines because when you trust something to do an analysis for you, you don't see the sausage being made. Wouldn't it be better to ask for an Excel sheet, for instance, that analyzes this for me, and you see the analysis afterwards as a resultant, with the sausage being made in front of you, you can check the equations, you can check how it's made instead of just trusting it.
Yeah, and I think that one of the things that I do with my students is I always have them, asking ChatGPT to explain how they did stuff. Show me the Python code that you used to do this. You could do it the same thing with the Excel sheet. But I would argue that if we're not there now, we will be very soon, where it'll just be unbelievably trustworthy. Just like when you ask Excel to do something for you, you kind of don't ask Excel to explain to you, how did you do every calculation? How do I know that you did everything right? You just assume that it's going to, right? You're not checking it. You're hoping that it's validated, right? And I think we're going to see the same thing with these tools very soon. I mean, right now, like I've done, thousands of experiments now using it, including with all my students and teachers that I've done in workshops the last 6 months, and I see no evidence that. I mean, it gets wrong. It gives wrong information sometimes, but it's because. But you can figure out why it's doing it, right? Like so, I can tell it to find all the maxima values, and sometimes it finds maxima that weren't the maxima that I intended it to find, right? They are maxima. I just didn't put the right constraints in to make sure that it only found maxima that were associated with the phenomena that I wanted to find. It found like there was maxima in this noise, right? And it would choose one of those points. So yeah, you still have to check it.
Yeah, indeed. I would say you design so many of these experiments. It's great, but it's because we already know how to do it. So we are impressed how this big data it can be analyzed for us. But the student, they don't even starting from scratch. I don't think they learn. Like I teach in this intro level class for more than 10 years. They even having problem to draw the vector addition. Now I even gave in a piece of paper. Let them draw it alone. They won't draw it. And they have difficulty if I walk around. They randomly scale the vector on their own, Okay, so that's the first concern I have because we know how data analysis is done. We were impressed by it. Yeah. But the student, if they don't even know how to do it, they may have even problem to know. But I would say it will be a good, outside of the classroom, they want to learn more. It will be a good exercise for a student.
And I think that we have to figure out how to incorporate it in different groups. So I had a group of 30 high school kids this summer that I did a week's worth of this stuff. much more difficult than what we talked about today. And every kid just, loved it and went through it. And, but they were all super talented, bright kids who basically said they learned more in a week than they did in a year of AP Physics in high school using these approaches.
But I have a second part I haven't finished. If one day they start all using the cell phone, school will say, oh, you can do experiment on your cell phone. We don't need to buy the equipment for you. We even can do this in your dormitory. We don't even need to provide you the laboratory facility for experiment.
I suppose it's almost equivalent to allowing a student to run before they can walk. We give them these powerful tools without oversight, and they can run, but they don't know how they walk to get there.
Yeah. And I think, we have to figure out how to help them do that. But one of the things I'll tell you that would be a wonderful thing here to do at Fresno State is, and I did this with kids at Morehouse College, is they all want real world kind of problem solving experience. And this is so important in student learning, right? And if you go to a place like Harvey Mudd, right, this is like the centerpiece of what they do, right? Except you don't have, $100,000 for every couple students to do their senior research projects, right? But with AI and this, they can do stuff that's better than what everybody's been doing at Harvey Mudd, in Stanford and MIT for the last, 5 years, because they can now do incredible experiments, right? So I had a kid at Morehouse College, and he was using his phone, and he was placing it at different locations on his body and his back, and he was measuring the vibrations associated with his cardiac cycle and looking at how he could basically take an image, through the vibrations that he was measuring on it, right? And he needed nothing else, no other special equipment, right? And so this is potentially a way that you can do, a place we can start is with some of the more advanced classes, some of the, research kind of things that students can do, and it really opens up those opportunities as well. I mean, I ultimately want it to be for the, raising the floor for everybody, but I think those will be things that are challenges that we got to figure out. What are the aspects of it, and how do we use them to help students that are, not, at the highest performance level, that are self-motivated and driven and really trying to do, ready to do complex stuff.
I'm associated with a community college, Reedley College, and they could really use something like this to make it, to connect with these kids, but just some of them, they're stumbling, and it would help them see a lot more exciting results more quickly, so.
What I did this summer is I had 3 summer students, and what they were working on was essentially an AI that basically was an interacting AI with your phone, so that instead of like what I did today, where I walked people through activities, the phone actually looks at the data in real time, interacts with the student, gives them feedback on it, and will actually help tutor them through.
Maybe instructor for.
Well, I think that the challenge is that, at least in high schools, about half the students who would like to take physics can't, because those physics teachers don't exist. Okay, and so there's a huge gap that could be addressed by this.
Questions? John?
Got an observation and sort of a two-part question. First off, some of the things that you were having these kids do, just asking ChatGPT, were large parts of graduate courses that I took back in the 80s. Things like digital signal processing, how to program this on a mini computer, soon to be a workstation, soon to be a personal computer. So it's, and even the heart rate variability thing was a big chunk of one of my friend's doctoral dissertations, going another step beyond that. But the question I have is sort of two parts. Do you have any idea what the carbon footprint is for getting this much computation done? And have you asked ChatGPT what is the carbon footprint for doing this?
Yeah, I've looked at this very carefully and thoughtfully, and I can tell you that I use ChatGPT, for 3 hours a day maybe, in what I do, and that and I look at the different activities that I did and what the energy consumption is of that, and I burn like 5 times more energy driving to work each day. So the reality is I'm a heavy user, and I don't come close, it doesn't come close to making a significant difference on my carbon footprint.
Okay.
Now, I caveat that with, I drive a SUV. But the bottom line is there's a lot of people making that argument, and the reality is that relatively it's a very small amount compared to other things that we do.
It's a question to ask, and I'm glad it hasn't been answered.
Other questions? Let's ask our speaker again.